K-means it's an unsupervised machine learning algorithm and it is used for clustering. And its goal is very simple: group similar data points together into K cluster. So, for example, suppose these are your data points and you want to group into three clusters. This machine learning algorithm will group them into three clusters: cluster A, B, and C. Now, before I explain the K-mean algorithm, let's understand few key terms. Centroid. So suppose you have a data set that consists of three features: age, income, and debt. And you want to find centroid of these points. And let's say I plot these points over here. This is my point P1, P2, P3, P4, corresponding to each one of these 4 points. So the way you find centroid is you take these age values and you add them all together and you divide by the total number of records. In this case, 21 plus 42 plus 56 plus 24 divided by 4. This one. And then you do the same thing with income. You take all these numbers, you add them together and you divide by 4. And you do the same thing with the third feature, debt. 10 plus 0 plus 80 plus 0 divided by 4. And your answer will come out to be this right here. So this point is my centroid for this data set. So this would be somewhere like this right here. Distance. Suppose you have to find distance between two data points. Let's say my two data points is P1, this one right here, that would be this, and P2, that would be this point right here. And I want to know the distance between these 2 points. In this case, I'll use Euclidean distance formula. So your distance between the 2 points P1, P2 would be 21 minus 56 whole square. In other words, this number minus 56 square, that would be this term, plus then you do 30 minus 50 square, 30 minus 50 square, plus 10 minus 80 square. 10 minus 80 square, and then you underroot the whole expression. This will give you the distance between P1 and P2, this right here. And now the k-mean algorithm. Suppose you want to find two clusters from these set of points. So the first thing you do, you start with all your points. Step 2, now you randomly choose two centroid. These two centroid, they do not have to be part of your data points. So I just randomly pick up these 2 points right here. And now you draw a half line between the two centroids. So these are my two centroids, this one. Connect these two together with this line. And then you draw a line that is cutting this line into half. And this should be 90 degree. Step 4. Now you assign points to the cluster that are closest to it. So in this particular instance, you can see all the points on this side, they would be closest to this cluster. So assign this point to this cluster, assign this to this. Same thing on this way. This one assigned to this one gets assigned to this, and this one gets assigned to this, and same thing with this and this. So all these points, this, they get green, and these 2 points, they get assigned red. And now we have two clusters, these two right here and this one right here. And now you find the centroid of these two new clusters. So let's say the centroid for this cluster is this, and let's say the centroid for this cluster is this. And now you repeat the process. You draw a half line between the two centroids. So this is my first centroid, second centroid. Connect these two centroids with a line. Draw a half line between them. This line would right here would actually divide this line into half, and this would be 90 degree. Now the points that are closest to this centroid, assign them to this centroid. So this one will get assigned to this one, this will get assigned to this, and this will get assigned to this because these 3 points are closest to this. Same thing with this one. This one will get assigned to this will get assigned to this, and this to this, and this one to this. So all these 4 points right here, they would be assigned to this centroid. And so now we have new cluster. This is my first cluster right here, and this is my second cluster. And this point right here, it changed cluster. Initially it was in this cluster, now it came to this cluster. And now you repeat the process again. You take this cluster over here, you find the centroid for this cluster, let's say it is this one, and then you do the same thing, take this cluster right here, find the centroid for this, and let's say it is this right here. Now you find the half line between these two centroids. So connect these two centroids, draw a half line in between them. All the points that fall on this side, they will be assigned to this centroid. So this point will come on this side. This point will be assigned to this. This will be assigned to this. This will be assigned to this. Same thing over here. All the points that are on this side, they'll be assigned to these centroid. And that's because these points are closest to this centroid. So now you notice, you'll see this is a point that actually changed its cluster. It's going from the old cluster to this new cluster right here. And now you have a new cluster. This one and this one. And then you do the same thing again. You find the centroid of this points right here. Let's say the centroid comes out to be this, and you do the same thing over here. You find the centroid of this cluster right here. And let's say it is this. You draw a line between them, draw a half line, and then you find which points are closest to which centroid. Well, this one is closest to this is closest to this one is closest to this, and same thing with this. Same thing over here. Now, if you notice, there is no change happening over here. All the points that are assigned to the cluster, they are still assigned to the same cluster. In other words, there is no change, and when there is no change, you stop. So this is your final two clusters, this one and this one right here. Now the question is, how do you find the right k? If you remember from our algorithm, we start with k equal to 2. Well, we could have picked up k equal to 3, 4, 5. So what is the right k? Well, in order to determine the right k, we use something called elbow method. In order to understand elbow method, you have to understand within cluster sum of square. This is the sum of the square distance between each data point and its clustered centroid. Another name for that is sum of squared error, SSE. So let's understand this through a simple example. So suppose this is my data point and I'm finding two clusters, k equal to 2. So this is my cluster 1, cluster 2. So in this case, my WCSS will be equal to this distance square plus this distance square plus this distance square plus this distance square plus this distance square. That would be this right here. Plus, then you do the same thing with the second cluster. This distance square plus this distance square plus this. You basically add all of them together, and that would be this right here. So the sum of this distance square plus the sum of this distance square, that would be this plus this, that will give you your WCSS for k equal to 2. So this represents my within cluster sum of squares when your k equal to 2. Now let's find WCSS for only one cluster. So suppose I have these 5 data points, P1, P2, P3, P4, and P5, and I plot these points over here. Now in this case, all the points are assigned to just one cluster. So this is my one giant cluster right here. So first thing you do, you find the centroid for this cluster. So in this case, you add 1 plus 1 plus 4 plus 5 plus 6. Basically, I'm just taking this first point, 1 plus 1 plus 4 plus 5 plus 6. That will be this. Divide by the total number of points, that will be 5. And you do the same thing with the next coordinate. And this will give you the point, the centroid point right here. So your centroid is 3.4 comma 2.6. That would be somewhere, maybe somewhere over here. So let's say this is your centroid. And now you calculate the distance for each one of the points to the centroid. So let's do this one first. So in this case, this distance, that would be equal to 1 minus 3.4. 1 because the coordinate of P1 is 1 comma 1. And the coordinate of this was 3.4 comma 2.6. So you do 1 minus 3.4 square plus 1 minus 2.6 square, and then you add the answer, and your answer will come out to be 8.32. So this is the distance square from here to here. Then you do the same thing with this point and this point and this point and then this point. So I calculate the distance over here, 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 and here. So this is the distance square, this one right here. Now you just add all the distance together. So in this case, when you add all the distance that was squared, your answer will come out to be 26.40. So this is your WCSS when your k equal to 1. In other words, when you have just one cluster. And now let's calculate WCSS for k equal to 2 clusters. So let's say my two clusters are these, this one and this one. So in this particular instance, my P1, P2, basically they are the same point as the previous one. So centroid for cluster A, using the same expression, will be 1 plus 1 divided by 2 and 1 plus 2 divided by 2. So calculate the centroid for P1 and P2, and the answer is this right here. And same thing with your other centroid, this will be this. So let's say this is your centroid A, and let's call this thing as centroid B. So centroid for A is this, and centroid for cluster B is this right here. Then you find the distance. So let's say my centroid is over here. Let's just call this thing as cross. And same thing, let's say this is over here. So now you find this distance and this distance, and you square each one of them. So I'm finding the distance, I'm squaring each one of them, and then I find WCSS for my cluster A. So in this case, WCSS for cluster A, you basically add these two numbers together, these two distance squared together, and the answer is 0.50. Now you do the same thing. You find this distance, you find this distance, and you find this distance, and you square each one of this distance. This is exactly what I'm doing over here. Right here, right here, and right here. And then you just add all the distance together, all the square distance together. So in this case, I added all the square distance together, and that gave me WCSS for cluster B. That would be this right here. Then I add my WCSS for cluster A and cluster B together, and the answer comes out to be 3.16. And if you notice, your WCSS, it went down as your cluster went up. So previously, my WCSS was 26.40, and now my WCSS is 3.16. So the observation is this: your WCSS, it would decrease as your K increases. So let's say this is my data point, and I draw one cluster for this. So in this case, my K is equal to 1. My WCSS is going to be the maximum in this case. So this is the formula for WCSS for this particular instance. Now, and when your K equal to 2, in this instance, your WCSS would be equal to the WCSS for this plus WCSS for this, which will be this right here. And this WCSS would be a little bit smaller over here. Now, when your K equal to 3, your WCSS is going to be equal to the within cluster sum of square for the first cluster, for the second cluster, and for the third cluster. These ones right here. And your WCSS will keep going down as your number of clusters goes up. Now, when you plot your WCSS against your K value, you are going to notice that as your K increases from 1 to 2 to 3, your WCSS, it will drop. So there'll be a big drop initially. There's been another drop after that, but the drop would be a little smaller. And then there'll be another drop right here. It'll be smaller. And the keep each time when you increase your K, your drop will keep getting smaller and smaller. At some point, your drop is going to be way smaller. So in this instance right here, you can see that going from K from 2 to 3, there was a drop, but the drop from 3 to 4 is smaller than the drop from 2 to 3. So this point right here, this is called an elbow. And the reason it is called elbow, because it looks like the hand or the elbow of an hand. So in this particular instance, your K equal to 3 would be the right number of clusters. So choosing K equal to 3 clusters, that would be a good number. So why is WCSS so important? Well, that's because it measures how compact your cluster is. A cluster that has a small WCSS is going to be more compact and better than a cluster with a large WCSS. So let's understand this through this example. In this particular instance, you can see that I have this cluster and this cluster, and look at them, they are more compact over here. Here my WCSS is 15.89. In this particular instance, again I have three clusters, but look at that, they are not very compact, they're kind of like loosely spread out. And here in this particular instance, my WCSS is 129.73, a big number over here, a smaller number over here. We can also use WCSS to find the optimal number of clusters. We saw that in a previous slide. The value of K that gave you the smallest WCSS was the best value. Now, always scale, in other words, standardize your data in K-means algorithm. Otherwise, your features that are using big numbers, that have a big range of numbers, they are going to influence your K-mean clusters. So let's understand this through a simple example. I have two cases. In case one, my data is not standardized, it is not scaled. In my case two, the data is scaled. It is all the values are between 10 to 100. You can see that over here. So let's say you want to calculate the distance for case one. So let's say this is my data point x and this is my data point y. So the distance between x and y using Euclidean formula is given by this expression right here. And you can see 21 minus 56 square. This number is very small compared with this number, 30,000 minus 50,000 square. Now your income feature, this is going to dominate, and that's because of this big range of numbers right here. In the case 2, when I calculate my distance between x and y, let's say this is x, And this is why, in this case, you can see the age is 21 minus 56 squared and your income is 30 minus 50 squared. You can see that neither one of these columns, neither one of these values or features are dominating. They're both producing, they both are having the same level of influence in your distance metric. Now, Python has a scikit-learn package that allows you to find these clusters using k-means. So suppose these are my data points, 5 data points. You specify your number of clusters in this function. So in this case, my number of clusters is 2. You feed your data x to that. And this way, it prints out your labels and also the centroid and also your WCSS. So in this particular instance, my cluster labels are 1, 1, 0, 0, 0. That would be this right here. So this is 1, this is 1, 0, 0, 0. So 1, 1, basically they refer to the same class. So these 2 points, they belong to the same class. These are your 1, and these 3 right here, they are in your class 0 right here. And these is your centroid point.